Now, let's move here to normal Gaussian distribution. By the way, any questions so far? So now let's talk about this normal or Gaussian distribution, okay? So it's, or AKA bell curve. So those are all same words. So if it's a normal distribution, if it's a Gaussian distribution, bell curve, they are indicating all same thing. Long time ago, they thought a distribution that looks like this is a normal thing. If a distribution looked like that, maybe it's an evil thing, or I don't know. So that's the reason why they called it normal distribution. And later on, Gauss, that genius from, I think he was from Germany, the area. Anyway, so he came up with an equation to express how this shape looks like. So after its name, it's also called Gaussian, and bell curve, it looks like a bell. So these kind of distribution, normal Gaussian or bell curve, that is determined by two terms, the mean value and the standard deviation. So mean mu and the standard deviation, this is the mean and standard. So if you know these two numbers, then you can define this distribution, all right? So normal distribution is determined by just two numbers, mean and the standard deviation. And this is how you just mathematically write that. So whatever measurement x is following a normal distribution that has mu, the mean, comma, and standard deviation, all right? And the property of this normal distribution is that the mean and the median and the mode, they're identical. They're just the same, all right? It's just the center of this distribution. And you can definitely tell it's a symmetric distribution with respect to that center point or the mean value. And like I just said, you can define the distribution by using only two variables, mu and sigma. So if we take a look at this distribution, these two down here, say I have measured the height of this section, and I have measured the height of the folks in Zoom, and that was here. All right, and I just plotted as a histogram. And from here, we can definitely see the mean values are different. The guys in Zoom are slightly taller than you guys here, or something like that, okay? But the distribution, the spread out of the measurement are similar, right? So from here, you can tell the distribution is same, mu1 and mu2, but the mean values are different, right? And the one down here, we have three different distributions, this one and that one, and this one is number 3. And the mu's are all the same. The average or the mean value are all the same. On the other hand, which one has the largest values? Sigma 1, sigma 2, or sigma 3? Can anybody tell me?
Sigma 3.
Sigma 3, all right? So sigma, the standard deviation, is related to how your data is spread out from your center or your mean value, okay? So I really want you to not get confused about this concept anymore, because most of you understand this, but sometimes I see some students get confused. Oh, sigma is small, so it's spread out. From now on, let's make sure the larger standard deviation you have, the larger the spread out the distribution you have with respect to your mean value, okay? So this one here is something that I want you to have in your head. Memorize these numbers, all right? And I want you to understand the concept behind here, all right? So for any normal distribution or any bell curve, this property works. 68% of your measurement is going to fall between plus and minus 1 standard deviation from your mean value. So 68% of your measurement is going to be in this interval if your property is following a normal distribution, okay? In other words, this area is going to be about 70% of this whole area. This whole area is 100, let's say. Then this area is 70, okay? If you're a visual learner, maybe you can think like that too. Or the meaning is, if you have measured a resistor, you measured 1,000 resistor, same resistor, say 1K resistor, but they're not exactly 1K, right? It's like 992, 10, 13, or whatever. And then you drew that distribution. Then 70% of your measurement is going to be within this range, plus and minus 1 standard deviation from your mean value. That's what I'm trying to say, okay? 68%. And 95% of your measurement is going to be within 2 standard deviation from your center value. So this is 2 standard deviation. This is 2 standard deviation, okay? So 95% of your measurement is going to fall within this range that is plus and minus 2 standard deviation from your mean value, okay? That's a property of normal distribution, Gaussian distribution bell curve. And 99.7% of your measurement is going to be between plus and minus 3 standard deviations. So in other words, this area is 99.7 out of this whole 100. Okay? In other words, it's really hard to find a value that is outside of this plus and minus 3 standard deviation. It's really rare, right? Only 0.3% of your total population is going to be in that kind of regime, okay? So it's a super outlier. So have these numbers in your mind and you're going to look smart. And we'll talk about how to look smart having these in your mind, okay? So now, when the distribution follows a normal distribution, we know the approximate shape of this distribution from the mean and the standard deviation, right? Because that's the 2 values determines the shape. And then you may want to know where the individual value is relatively located from within the total distribution. Okay, so just bear with me. And in order to kind of answer that question, people came up with a new concept or a slightly updated concept called standard normal distribution. Okay, and what this is your original measurement x that follows a normal distribution, which has a mu as a mean and sigma as a standard deviation, that can be transformed into a new variable y by multiplying a and adding b to your original measurement. And this y is going to follow a new normal distribution that has a times mu plus b and a squared sigma squared. That's just the mathematical property of these normal distributions, okay? So in other words, The meaning here is you can shift and scale the distribution, normal distribution, into a standard normal distribution. If it is a normal distribution, say this is a normal distribution, then if you squeeze that in to make it like a thinner one, then but still that is going to be a normal distribution. If you spread this thing out like that, then still it's going to be a normal distribution. Or if you just shift this whole thing to here like that, still it's a normal distribution. All right. So adding a number is shifting this left or right, and multiplying is spreading that out or making it thinner or like that. All right. So it's shifting or scaling. So all these normal distributions can be scaled and shift so that it has a 0 as your mean and 1 as your standard deviation. They all have different standard deviation. For example, say this is a measurement of the height of the student in this class. Say this is the distance of your hometown from here. Maybe it's more spread out, right? And I don't know, this one, say it's another distribution, okay? But they're all normal distributions. And all those different distributions can be scaled into a standard normal distribution that has a mean value of 0 and standard deviation is 1, okay? That's the concept here. And how you do that? You use a Z transform. So what you want to do is you want to make mu go to 0 and sigma go to 1. That's what you want to do from these distribution. You want to change that to 0 and 1 by defining a new variable that is Z is x minus mu divided by sigma. By using this kind of formula, you will be able to transform these into a standard normal distribution. And let's try an example. Say the exam result was following a normal distribution, and the average was 70 and the standard deviation was 5. Let's just assume like that. And then naturally you will ask about this question. Say you got 75 points. Am I good or bad? How good? How bad? 65. Am I top 5%? Or you want to know where you are within that distribution. So here comes these numbers that's going to help you. So 68, 90, 95, and 100 almost. So I am here 75. That means, and I just learned that this area is 68%, right? That means this here is what? 34. And because this whole thing is 100 and they're symmetric, this is 50. So this here is what? It's 16. So about 16% of students are ahead of me if I got 75 from that exam. Your top 16%. Okay? And if you got 65, it's easy. It's just the opposite, right? Symmetric. So this area is 16%. So your bottom 16. And what if you got 80? You're here. Then that is 2 standard deviation from your mean value, right? Your standard deviation was 5. So this area is what? Yeah, That's 95. So here and there is total 5, right? So just this portion is going to be 2.5. Got that? So now you're top 2.5%. All right? So if you have that kind of sense, okay, this is a normal distribution, and I know the mean, and I know the standard deviation, then if you remember these numbers, then you will be able to have like a ballpark number of where you are or anything like that. And that's going to make you look smart. All right. So now let's try with real numbers. Okay, so same thing, exam, normal distribution 70 and 5 are the mean and the standard deviation. And you want to find out where am I? You're going to be around here. Any guess? Like top, what percent? 40? Yeah, I'll go 42. Let's see. So you want to find out what is the area of this hatched area, right? So x minus mu divided by sigma, that's your z, right? And your x is what? X is 72 minus mu is 70. Let me just pull this down here, all right? Divided by sigma, which is 5. So that is 0.4, right? Okay, so your z is now 0.4. What do we do with that value? We go to this table. And what this table shows is if your z, say for example, let's try, if your z value happened to be 0.65, 0.6 and 5, then this colored area is what? It is going to be this value. So it's going to be 0.2579. That's how you read this table. Okay, so in our case, our z was what? Is 0.4. So what shall we do? We look for 0.4, which is 0.40. So it's going to be this value. So if your z were 0.4, then this colored area is going to be 0.34458. Got that? So you are here, which is 0.4. Colored area is about 34%. So if you, that means if you got X, your score was 72, then from this whole distribution, you are top 34%. Okay? So how this thing works is you have your original X, whatever test score, whatever measurement, things like that. You convert that into Z, and then you use the table, and then you correlate that back into the real thing. All right? That's how you use this Z score or the normal distribution, the standard normal distribution. And there also can be another question. Okay, so where should I be at? You want to be top 10% of this class. What you want to do is you want to make this area to be what? 0.1. And you want to find out that Z. Okay, so 0.1 is here, this one. That's close to 0.1, right? that means your Z, the corresponding Z is 1.2 and 8. So your Z should be 1.28. Okay, so if your Z is here is 1.28, then the area that is above that is 0.1. Okay, so now we're going to use Z is 1.28 from table. So next step is you correlate back into the original value. And how do we do that? We use that formula, x minus mu divided by sigma. So your Z is 1.28, and x is what you want to find out. Mu was 70. Is that right? Yeah, mu is 70 and sigma is 5. So divided by 5, you do the math. And that is 70 plus 1.28 times 5, and that is 76.4. So if you get 76.4 points, then you'll be the top 10% from the given distribution. All right? That's how you correlate your real data into the distribution, where you are located or something like that. You just move back and forth. All right?